The topic today is the optical scheme to implement POVM measurements. So here, as usual, we will consider the polarization qubits, and we will also consider the path degree of freedom of the photon. So that will be dual rail qubit or some other form of qubit. So we will see how when it is revealed. So the state psi of the qubit can be written as alpha horizontal plus beta vertical, where alpha and beta are complex numbers and H and V are horizontal and vertical polarizations. Alpha mod square plus beta mod square equals 1. That is for the normalization. Now we take a beam splitter, and this is a polarizing beam splitter. So what it does is, if the horizontal polarization is coming in, it will let it go. And if vertical polarization is coming in, then it will reflect it. So vertical will go vertically up and horizontal will go horizontally, but horizontal will go straight. So if we send state psi here, then H will go here and V will go there, and we perform measurements and we get the alpha mod square and beta mod square. This whole thing can be thought of in the following way. We have one path of input path of the beam splitter. Let us call it state A. If the photon is coming in this path, then we are calling it in the state A. And there is another path which we are not using for the time being, but there was a path, so that's state B. So these are input. The output, we are naming the straight path as same path and the reflected path as a different path. So output A and B we have. So the initial state can be thought of as state of a photon in 2 degrees of freedom. One is the polarization, other is the position basis. So the total state, initial state input, is psi tensor A. So psi is the polarization state of the photon, and A is the spatial state path information. That is equal to alpha HA plus beta VA. Now, when we pass it through polarizing beam splitter, then HA goes to HA. It will remain in the same path, but VA will go to VB. HB will remain same, HB, and VB will become VA. Now, what is the action of the polarizing beam splitter on psi tensor A? So psi tensor A will go to alpha, HA remains HA, plus VA becomes VB. After that, we perform intensity measurements in A and B. That is, we put detectors which do not discriminate between the polarization, but they just see whether the photon was in A or B. So we are performing measurement in the spatial modes. So whether the photon was in A or B, we perform measurement that, and accordingly we know whether the probability of getting the photon in A is alpha mod square, and probability of getting in B is beta mod square, and which is same as probability of getting in H and probability of getting in V. So what we have done here is, we had a system that is the polarization. We have an ancilla that is the spatial degree of freedom, path degree of freedom, and we take these two systems together. We use a unitary transformation to couple those two, and then we perform measurement on the ancilla. And in that fashion, we are performing measurement on the polarization indirectly. But here the interaction was very, very strong between the system and the ancilla. That's why this effectively became a projective measurement. Now, how do we perform POVM on such system? On the same system, if we want to perform POVM, how will it go? So for simplicity, we take a POVM where the measurement operators are K0 and K1. Okay, such that K0 dagger K0 plus K1 dagger K1 equals identity. These are measurement operators, these are not effects. In fact, for these given measurement operators, K0 dagger K0 will be one effect and K1 dagger K1 will be another effect. So for given measurement operators, it's easy to find the effects. Now we want to find an optical setup which can implement this measurement operator. So from our earlier treatment, when we are given measurement operators, we know that we have to consider system and ancilla. The ordering, the total Hilbert space will be the Hilbert space of the ancilla times the Hilbert space of the system. We have to choose the state of the ancilla psi A initial state to be 0 state. In this case, it will be just path A. And we have to have a unitary acting on the two. And the unitary is chosen in such a way that the first block is K0, second block is K1. And then there are two blocks, let us call them U12 and U22. All of these four are 2 by 2 matrices. K0 and K1 are given to us. U12 and U22 are arbitrary in such a way that the total matrix U becomes a unitary. So let us say we have U12 and U22. Now, how to implement this arbitrary unitary on the polarization and path degree of freedom in a combined fashion is a challenge. So let us tackle that problem first. Let us say we are given a unitary U, which is of the form A, B, C, D, where A, B, C, and D are 2 by 2 matrices, complex matrices, such that the total U is a unitary. So if U is a unitary, then U times U dagger, which is A, sorry, my notations are slightly different. I want to stick to them. B, C, B, C, D, A dagger, B dagger, C dagger, and D dagger. The product will be A dagger plus B dagger, A C dagger plus B D dagger, the Hessian conjugate of that, and C dagger plus D dagger. So this is the matrix we get when we multiply U with U dagger in terms of A, B, C, and D matrices. And we know this must be equal to identity and 0 and 0. 2 by 2 identity, 2 by 2 0, 2 by 2 0, and 2 by 2 identity. So from here we get information that A dagger plus B dagger must be identity, and same as C dagger plus D dagger. This implies that A dagger equals 1 minus B dagger, and C dagger equals 1 minus D dagger. So it means A dagger commute with B dagger. Similarly, C dagger commute with D dagger. If two operators commute, then there must be a common unitary which can diagonalize both of them. So it means we have L1 A dagger, L1 dagger. Since A times A dagger is a positive matrix, positive operator, so the eigenvalue will be real. So we are writing diagonal matrices as dA square. So it can be real and positive matrix. Similarly, L1 B dagger, L1 dagger is dB square. Here we can have difference L2 C dagger, L2 dagger as dC square, and L2 D dagger L2 dagger as D square. For the time being, they just look mathematical, but trust me, this will become very interesting result soon. So till now, we just use U dagger. If we use U dagger, U equals identity. That will be A dagger, C dagger, B dagger, D dagger, A, B, C, D. It becomes A dagger A plus C dagger C. We don't care about the off diagonal terms. We did not use it in the previous one, so we will not use it here. B dagger B plus D dagger D, something here, and this must be equal to identity. Identity is 0, 0. From here we can see that A dagger A commute with C dagger C, and B dagger B commute with D dagger D. It means we can have R2, some unitary R2, A dagger A equals R2 dagger equals dA square. The spectrum of A dagger A and A dagger will remain same in this case. And R2 C dagger C, R2 dagger as dC square. R2 B dagger B, R2, that was R1, sorry. The naming does not matter, but I just want to be consistent with the notes so that later on if we use them, we don't make a mistake. dB square and R2 D dagger D, R2 dagger equals D square. Now, if let us say if we have a unitary W with such that W1, let us say, such that X dagger W1 is dx square and W2 X dagger X W2 dagger equals dx square then we can write W1 X W2 dagger as dx. This is called singular value decomposition. One should read the proof of this. This is a very beautiful theorem. So if we have two unitary operators W1 and W2 which diagonalizes X dagger and X dagger X, then W1 and W2 are the left and right eigenvectors of X, and we can diagonalize X in this fashion and we get dx, which is the matrix of singular values, diagonal matrix. And this theorem holds for any dimension of X. X need not be one square matrix, it can be rectangular matrix, it can be anything. So why we are mentioning this thing? Because from our analysis so far, we have L1 which diagonalizes A dagger and we have R1 which diagonalizes A dagger A. So it means we have L1 A R1 dagger to be dA. Similarly, we have L1 diagonalizing B and R2 diagonalizing B dagger B. So L1 B R2 dagger equals dB. L2 C R1 dagger equals dC and L2 D R2 dagger equals dd. So D was R2 here and L2 and D2. So what we have is A can be written as L1 dagger dA R1 dagger. B can be written as L1 B dB R2. Not here. C is L2 dagger DC R1 and D to be L2 dagger DD R2. So this implies that U can be written as L1 dagger DA R, L1 dagger DB R2. L2 dagger DC R1 and L2 dagger DD R2. Or we can write it as product of three matrices, that is L1 dagger, L2 dagger 0 0, DA, DB, DB, DC, and DD R1, R2. Now, for a moment, we should consider what we have done so far. We have a two-dimensional Hilbert space of the polarization qubit and two-dimensional Hilbert space of the path states. So the basis we have chosen is H8 tensor. HB is the total Hilbert space. So the basis is AH, AV, BH, BV. So it means the L1 vector is acting on states A tensor psi, where psi is the polarization state, but the path is fixed A. So L1 is acting only in the A subspace. Similarly, L2 is acting only in the B subspace. Similarly, R1 is acting only on A subspace, subspace corresponding to A, and L2, R2 is acting on the states with B subspace. So these L1, L2, R1, R2 are the unitary operators acting on the polarization states of light, but when they are in specific path. So R1 and L1 will act on polarization when they are in path A, and R2 and L2 will act on polarization when they are in path B. So these are operations acting only on the polarization qubits, but in a specific path. And this is a unitary. L1 and L2 were unitary, R1 and R2 were unitary, so the total matrix is also unitary. Total matrix is also unitary, this one and this one is also unitary. And U is unitary, so this must be unitary in the middle. Now let us analyze the matrix of diagonals. Matrix of diagonals is DA. DA was the matrix of singular values of matrix A. Let us call them A1, A2, 2 by 2 matrix, and wherever I don't write an element, they are 0. Then we have B1, B2, we have C1, C2, and D1, D2. And it's a unitary matrix. First condition of a unitary matrix is every column and every row must be normalized. And A, B, C, D, all of them elements are real here. It means we have A1 square plus C1 square equals identity 1. This implies that we can assume A1 is cos of theta and B1 is, or C1 is sine of theta. Okay, we are fixing the sign here. Then this is what was about the first column. Now first row says A1 square plus B1 square is 1. Then we know A1 is cos theta. This implies that B1 must be sine theta, but it could be minus sine theta also. So instead of that, we just say B1 square is sine square theta. Now, if we consider the third column, it becomes B1 square plus D1 square is 1. This implies that D1 it can be D1 square is cos theta, cos square theta. Similarly, we can do with A2, C2, B2, D2, and instead of theta, we can say theta 1 here and theta 2 for the other one. So the matrix becomes theta 1 and cos of theta 2 plus minus sine of theta 1. We have to choose whether it's plus or minus, and plus minus sine of theta 2, then sine of theta 1, sine of theta 2, and cos of theta 1 plus minus and plus minus cos of theta 2. This is the form of the matrix we have. The first one we can choose on our wish, but other signs we cannot choose arbitrarily. Now, if we analyze it further, and it's very straightforward, but it might take a lot of time in the lecture to prove it. But if we look at it very carefully, we will see that if these have to be plus sign, then they must be negative sign here. So these two should have opposite signs. And if we want the whole thing to be unitary, then and this vector to be orthogonal to this vector, then this must be plus. So our matrix of diagonals will take this form: cos of theta 1, cos of theta 2 in the first block, minus sine of theta 1, minus sine of theta 2, sine of theta 1, sine of theta 2, and cos of theta 1, cos of theta 2. This becomes our canonical form for the matrix of diagonals. Since it is a matrix of cosines and sines, so it is called CS matrix. And with this, our unitary, which is L1 dagger, direct sum L2 dagger, and then CS matrix, and then R1 direct sum R2. This whole thing is called CS decomposition. Analyzing further this matrix, CS matrix, and I will just write C1, C2 for cos theta 1, cos theta 2, S1, S2, S1, S2 here, and C1, C2. And this can be written as identity, I times identity, I times identity, and identity. This is 2 by 2 identities. And then we have exponential of minus I theta 1, exponential of minus I theta 2, exponential of I theta 1, exponential of I theta 2. Identity minus I times identity minus I times identity and identity. There is 1 over root 2 here and 1 over root 2 here. So we can decompose this CS matrix into a matrix without thetas and a phase matrix and matrix without thetas. What we have done here so far is we have decomposed this matrix of diagonals, this CS matrix, into a matrix without any phase information theta and a matrix with diagonal matrix having the information about phases. This matrix is a beam splitter acting only on the path information A and B, irrespective of the polarization. It does not depend on polarization. Similarly, this matrix is the beam splitter matrix, and it does not depend on the polarization state. But this is a phase matrix which gives you phase of theta 1 and theta 2 to horizontal and vertical polarizations in the two different paths. So the CS matrix can be represented as a beam splitter where the path A and path B are coming, then they merge and they go. Here is the theta minus theta, and this is the theta. This is a wave plate which will give us theta 1 and theta 2 phases for horizontal and vertical polarizations. And here it will have minus sign in the phase, and this will have plus sign. So these two will give you the matrix, diagonal matrix of phases. And then we have another beam splitter, the beam splitter and beam splitter. In this way, we can implement this cosine and sine matrix. So now what is left is the R1, R2, L1, L2 matrices. In this representation, R1 and R2 acts on the state first, then the diagonal matrices, and then L1, L2. In the diagram, state goes from here. This is path A, this is path B. So first we apply R1 and R2, then we have our CS matrix, and then we apply L1 dagger and L2 dagger. In that way, we can implement an arbitrary four-dimensional unitary on polarization and path degree of freedom of a photon. Now, one can ask the question, how do we implement L1, L2, R1 and R2 matrices on the unitaries on the polarization? This can be achieved by using two half-wave plate and one quarter-wave plate, or two quarter-wave plates and one half-wave plate. That scheme is pretty well known and one can find it online. This L1, L2, R1, R2 can be implemented easily using quarter wave plates and half wave plates, and we are not going to discuss that in detail in this lecture. Now, once we know that any arbitrary unitary can be implemented by decomposing it into actions on polarization and action on the paths alone, then we consider our U, which contains the information about the measurement operators K0 and K1, and arbitrary matrices U12 and U22. By comparing this thing with the earlier discussion, we can see that K0 is L1 dagger dA, or let me write cos theta 1, cos theta 2, R1, and K1 is L2 dagger sin theta 1, sin theta 2, R1. So K0 and K1 are given to us. L1 and R1 are unitary matrices, L2 and R1 are unitary matrices, and there is a diagonal matrix. So this automatically becomes the singular value decomposition of matrix K0 and K1. So for a given K0, K1, we can always find L1, R1, and C1, C2. Similarly, for K1, we can find L2, R1, and S1, S2. From here, we have information about theta 1, theta 2, L1, L2, R1, and R2 is unknown. For simplicity, we can choose R1, R2 to be anything, and we can choose it to be identity also. Identity is a valid unitary matrix. Then our U12 will become L1 dagger minus S1 sin 1 minus sin 2 sin theta 2 and times the identity. So identity we don't need to write, and U22 becomes L2 dagger cos theta 1 cos theta 2 0. So in that way, by choosing R2 to be identity, we have made the choice of U12 and U22 to be easy. It's no longer arbitrary. It's the simplest we can find in our setup. Maybe if we are using different scheme to implement the unitaries, we can choose R2 to be different, so that the U12 and U22 are more easy to implement, and the whole scheme will look like the following. There's R1 and this is path A, so if the photon enters in the path A, then there's a beam splitter, there is a phase theta minus theta here and plus theta. So I'm just writing theta, but it contains theta 1 and theta 2 corresponding to H and V, and this can be implemented with wave plates. There is another beam splitter, and then we have L1 dagger, L2 dagger, and outcome. So we send the photon in this path, we perform the unitary U, which contains the information about K0 and K1, and after passing through all these things, the polarization state here will be proportional to K naught psi, and this is the psi state coming in, so it's 8 tensor psi, and K naught psi, and this will be K1 psi state coming. So if we just detect the number of photons coming in the upper mode or the lower mode, that will give us the probability P0, which is psi K0 dagger K0 psi, and P1, which is psi K1 dagger K1 psi. So in that way, we can implement these two effects POVM when the measurement operators were given to us. We can generalize this scheme to any number of POVM elements in a set. So in that way, this is very general scheme.